Our second example will be an inductor. So for our inductor, we'll have L voltage, current. And now our relationship, the voltage, is going to be writing it as L di dt. Now, again, because of how we wrote the voltage and the current, this is V naught when we complexify all these functions. When we take the derivative of, let's just remind ourselves that I of t is I naught e to the I omega t minus phi. It's one way to write it. That when we differentiate the current, we'll get a factor I omega I naught e to the I omega t minus phi. So let's write this again, separate this out a little bit. So we have I minus phi. Now, our fact that we want, first off, as before, we divide out by e to the I omega t. And so we have I omega I naught e to the minus I phi. Our goal is to find what the delta is for the phases and the amplitude. So now, again, we're going to do a similar argument that we did before. This side is real. We'll write the number I as e to the I pi over 2. So that's e to the I pi over 2 times omega times I naught times e to the minus I phi. And in order for this side to be real, then we have to have that e to the I pi over 2 times e to the minus I phi has to be 1. And that tells us that phi is equal to pi divided by 2. So then we have V naught equals omega L times I naught. And to get the modulus, this is telling us that V naught over I naught is equal to omega L. And that's precisely the modulus of Z. And so once again, our phase is equal to the phase of the complex number. So we'll write Z of L, Z e to the I delta. The modulus is omega L. And the phase is I pi over 2. And so there is our number, our impedance. Now, because e to the I pi over 2 is I, we can just write this as a complex, pure imaginary number, I omega L, which is the way that we'll use it.